Hello, I want to talk to you today about the improved memory layout I've done for the Pluto unikernel. So the idea, again, as I'll reiterate, is we want separate programs from the kernel, and what we need is a way of the kernel exposing functions so that our separate little mini programs can use functions. The way I set it out now is to have the functions we want to expose as a vector table of functions. I'll get to that in just a minute, but first I want to show what an example program will look like. So let's have a look at what an example program that you might want to construct would look like. What we need to do is import the exports header, which will expose the different functions in the kernel. I've labeled each kernel function with a PL prefix. So PL GPIO out turns an LED into an output pin. This is a normal for loop. We can set the LED, sleep, clear, and we go round in a loop. And here's our main program function. It goes in a special section called text.prog to make sure it goes at the beginning of the memory. Now let's have a look at the linker script. Got to change that a bit. So this is the linker script for a subprogram. Right, I'm not sure if this helps or not, but we now set the origin to a fixed address. I've used address hex 110,000 with a length of 256 kilobyte, which is the probably not a good number, but right. So as I said before, we want to put programs now into this fixed address in Flash. So we have to make sure our kernel doesn't intrude into that space. I haven't done any special checks, but I could probably enhance that so that it checks that. Text.prog, this is where the main program goes, and anything after that goes there. Let's just have a quick look at the disassembly of the program. Okay, points to note is that the main function I'm calling prog. This is the area of Flash that I want to put it into, which I've shown you before. We go down and forget the debug info. And well, this is just a disassembly. Now I've transferred that onto an SD card, and the binary is called blink.bin. So let's load the blink sketch into the RP2040. So I do load blink.bin. That's work, even though you can't see it very well because I've got a pretty ropey webcam. I'm going to run, take run, and you should see a blinking light for 5 seconds. Okay, that proves that point. I'm going to go to a slightly more complicated sketch, you call it, in which I have an image. Let's just have a look at the main program itself. Starters. So we've got this here. We're importing the exports we've got a blob, which I'll get through a little bit later. This is the image stored in a raw binary format that we want to put to the screen. And this is our main program here. Now, in order to get an image to a screen, we need to call the function PL0934 set filler. This sets a function pointer that the kernel calls periodically to refresh the screen. So you're going to need, now it has a default one, which you've seen as normal, but you can set your own specialized one, and this is what we're doing here because we want to display an image. So this is the function here, and you have to specify the function in a certain way. You take a buffer, some sort of, this is the storage area for whatever you want to display. In this case it's an image, and a slice. So a slice corresponds to a column on the display. We display one slice at a time. So it's pretty straightforward. We do a memory copy from the buffer, to the buffer, starting at a certain address calculated by the slice. Sorry, I got that wrong. When it copied to a buffer, where do we copy it from? Well, we need an offset from our image. Each slice is 240 pixels. Each pixel is 2 bytes, making 240 times 2, and this is the number we transfer. So we're basically copying this mysterious blob one column at a time. Let's have a look how we get this blob. So we need to put some kind of preprocessed bitmap into a blob binary file, and to do that we set up a little helper assembly file called blob.s. Now the new version of C that's coming out has an embed function, which should make things a lot easier, but I don't have a compiler that has embed, and in fact GCC hasn't incorporated the embed functionality in it. I'm looking forward to having embed, but in the meantime we just need to do some embedding ourselves, and this is kind of embedding. Okay, so we want to put this in the text section. We're calling it a blob. Make sure it's aligned to 4 bytes. Calling it blob, and the secret source in here is to ink bin this Pluto.raw file. So the Pluto.raw is a binary file that I've pre-processed an image to be suitable for the screen. So ink bin just basically says we'll take all that data and shove it in a binary. We denote the end of the blob because we need a size, I think. Yeah, we need a size, which is just the end minus the beginning. Just take a quick look at the make file. There's It's similar to the one for Blink, although you'll notice that there's a blob.o. We need to incorporate that blob. Let's take a quick look at the disassembled file. So we've got the prog, which is fairly similar to what we had last time. We've got our Pluto filler function. Notice that this occurs after the prog. We have to make absolutely sure that the prog appears, the main function appears in address hex 100 10,000. Then we have the blob here, which is a whole bunch of bytes, pretty meaningless. Goes on quite a way to the debug frame. We're not interested in that. And
wow, that's not very interesting.
Let's see what this looks like. This is quite exciting. Again, I put the binary onto the SD card, and I'm going to load image.bin. Okay, that's done that. And now I run the program. So this should display an interesting picture for 5 seconds and then return. So let's do that. And that's a picture of Pluto. It looks more impressive in real life because I say I've got a wonky old webcam, so you don't really see that much. Let's run it again for good measure. It's quite detailed when you look on the screen. That's that. I'm happy with that. Let's just have a look now at how we've rearranged the original kernel. An important file is exports.h. Get that right. So here, prog base, you recognize this number. This is where the subprogram goes on flash. This line here, we declare a type f pointer to be a function that takes nothing and returns a void. Now that's not strictly true. You can pass multiple parameters in where the function requires it, but that's the type def we want. So I've defined a PL exports T. This is going to be the exports table that we're going to shove somewhere. I'll tell you where in a minute. And the structure tells you all of the functions in the kernel that we want to import. I have a little magic number here, just so that we can locate the table in memory. Just so we have a quick look. There's a version number. I've decided that I would like a versioning of the layout, so that, for example, in later versions you can check that you've got sufficient functions for the program to work, and perhaps bail if the kernel is too early and that the user needs to update the kernel. Now you may recognize these that we've used memcopy, we've used set filler, GPIO out, GPIO function sleep, and reset filler to return things to normal. Let's have a look here. So there's some stuff that I've decided to do without. Now, okay, we're going to define here a variable called PL exports, which is actually a structure PL exports T, which we define above, and we're going to put this in a special section, Pluto exports. We want to make sure we get that in a specific place on the flash drive so that subprograms know where the export table is. And that's a little bit tricky. We ask ourselves the question, well, how do we call these functions? So as you see in the example, there's a function called PL_ILI9341 set filler. How do we call that? Well, I created a little helper definition, helper macro, and we're going to store the table at address 10,200, which is near the front of the flash. I've reserved a hex value of 200, which will store the boot 2 loader. You need space for the interrupt vector. You also need a little bit of space for the default interrupts, and you also need a little bit of space, tiny little space, for the binary information. I'll get onto that in a little bit. So basically you treat address 10,200 hex as a pointer to the export table, and then you take an offset from that given by the function name. So let us just see how set filler works. So I define a macro PL0934 set filler. Now that takes an address, and we compute an offset to get an actual address of where the ILI9341 set filler function is. Then we call that as a function with the address, and so on and so forth with all the rest of the functions. What else do I need to cover? Let me have a look at the linker script. Okay, this is a custom linker script. This is as before. Now this is mostly the standard Raspberry Pi linker script. I had to make a few adjustments. This is as before, the boot 2 is as before, the assertion is as before, and now I have added this section here, which I've called the front section. Ignore that, that doesn't exist. This is essentially as before. This is before. This is essentially as before, but I've kept it separate from the .txt section because after that I want to insert the Pluto exports, which, as you recall, Pluto exports is a section that I put in exports.h. Now there's a linker command. If I put an address after a section number, name rather, this will be the address that I want it to appear in Flash. And what do I want in that section? Well, I want the Pluto exports. So I put that in Flash. And the text section is as before, except that I've moved out the vectors and the binary info header. I think it's worth looking at having a quick look at the disassembled file, just to make sure everything is as we expect it to be. Now, the CMake file creates a disassembled file, although it doesn't quite print everything that I'm interested in. Now, the CMake file is a bit of a convoluted thing in the Raspberry Pi SDK, so I'm not quite sure how to get the disassembly that I want, but unfortunately it doesn't matter too much because I can make it myself.